I guess. All right, so Jordan wanted to talk about existence and uniqueness, which I think is probably a reasonable topic. So I have here problem one out of 2.3. I have the directions for problem one, and then I also have the existence and uniqueness theorem out of the textbook. Okay, so this was your question, right, Jordan?
Yeah.
Okay, so we want to find all the pairs of x naughts and y naughts for which this theorem applies, so that implies that the initial value problem blah 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 has a solution and is that solution is unique. Does the distinction between existence and uniqueness make sense to you guys?
Yes.
Yeah.
Okay, so let's try an example. Does there exist a number that's divisible by 2?
Yes.
Is such a number unique?
No.
No.
Good. Let's see. Is there a number which is divisible by 0?
No.
I mean, not in our current number system, right? Would such a number be unique if it did exist?
Theoretically, yes, although that's really hard to say.
Yeah, it's kind of hard to talk about whether or not something is unique if it doesn't exist. Does that sort of follow? So when we're talking about existence and uniqueness theorems, they're usually phrased as existence and then uniqueness, because the first question is there one of these? And then the next question is it the only one of these? Now, the reason that I care, like the fundamental reason that I'm doing differential equations at all, is that I want to be able to solve problems about the world, right? Like I want to be able to take one of Bridget's vats of cheese and know that if it's a certain temperature and a certain concentration of sugar and a certain blah blah blah, like whatever all the parameters are, right? If I have two basically identical tanks of stuff, my hope is that they would evolve in the same way, right? That I would end up with basically the same cheese every time I kind of started a tank this way. Does that kind of idea make sense? So if I thought about kind of in the one-dimensional case, right? I have like some kind of nonsense. You just have like some kind of response variable this way, right? And some kind of time variable this way. My hope is that if I have this case where I start here, that there's one and only one way for that thing to kind of go into the future. You guys see this? I would have real problems if there were two options for that and they did kind of wildly different things. You guys kind of with me on that? So my kind of things for which the existence and uniqueness theorem applies, say if I start this, it's going to have an evolution into the future that I can predict, and that prediction is going to be valid in some sense. Like it's going to be the only way that can go. You guys see that? So this is existence and not unique would look something like this. Existence and uniqueness would look like this, right? And then non-existence is a weirder one. That one looks like this. Don't overthink that one. You guys good with those distinctions? Okay, so let's kind of read our little theorem. So it says that if I have a function that's continuous on an open rectangle, okay, weird, that contains an initial value, then my IVP has at least one solution. And if f and its y derivative are continuous, then I have a unique solution. You guys with me on that? So let's look at our function here. So first things first, which part of this problem is playing that function f?
X squared plus y squared divided by sine x.
Okay. This is my function f of x and y, right? And I just want to know, when is that continuous, right? For kind of part A. I'm asking, when is x squared plus y squared over sine x continuous?
If x does not equal pi times an integer.
Yeah, basically I just need to know when the bottom's 0, right? So I can just kind of think to myself, like, badness, right? So the badness on this problem occurs when sine of x is 0. And then I need to kind of think about, okay, so when is sine 0? Let's see. Well, it's 0 at, what did you say about pi over 2, Sam?
I said pi times an integer. So like 0, pi, 2 pi, 3 pi.
Something like this.
Right.
Yep.
Yeah.
Perfect. One way I could think about that, right, is I'm looking for sine. Oops, that's a crappy drawing of sine. That's an even shittier drawing of sine. I'm just going to keep making crappy drawings of sine. Okay, so this one happens at 0, this one happens at pi, this one happens at 2 pi. So we can see that, yeah, okay, integer multiples of pi are going to cause me problems. So if I think about drawing the kind of space, right? So like here's all of space. And then I'm going to have these problems when x, right? Really, I should have said this. Right, so my thought bubble is like, okay, so sine of x is 0. That's going to be when x is pi over, or pi times n for an integer. So that's going to mean that I'm going to have a problem here for n is 0. I'm going to have another problem out here for pi. I'm going to have another problem out here at 2 pi. There's a problem back here at minus pi. That one got a little crammed, but you guys with me on this? Okay, so I need this thing to be continuous on a rectangle, right? You guys see that? So where are my rectangles going to be?
So for example, the first one could be like from 0 to pi on the x and from negative infinity to infinity on the y.
Yeah, good. So you could say, so this is a rectangle, right? That doesn't really quite fit with the theorem. The theorem says it has to be a finite rectangle. So we'd have to cut it at some, y values.
But since it's arbitrary, you could say there's an infinite number of finite rectangles that fill that space.
Yeah, essentially what I want to get at, though, is just that they can't cross the red lines. You guys see that? Okay. So that's kind of the first part of this. Now for the second part of this, let's see. So let me actually answer that question. I'm supposed to find all the x naughts and y naughts for which theorem 2.3.1 implies that the initial value problem has a solution, right? And so my x naught, y naughts are literally the set of points x and y with x not equal to pi n for n in Z. Maybe just in keeping with notation, we'll do that. So this is the answer to part A. Everybody with me on those? Okay. Now, how about when is this solution unique? What else do I need?
You take the partial derivative with respect to y of our f of x and y.
Good. So for part B, I already know when f is continuous, right? So I need to ask, when is fy continuous? So that's going to be the partial with respect to y of this thing. Everybody with me on that? Okay. Now this is the part that's maybe going to get a little hard. How do you differentiate this with respect to y?
Hold all x terms constant and then just differentiate it like you normally would.
Okay. So this is the same thing as taking the partial with respect to y of x squared over sine x plus y squared over sine x. Maybe?
Yep.
Is that a thing we can do with fractions? Do you guys remember how fractions work?
Yep, you can do that
Yep.
as long as it's not on the bottom.
Cool. All right, so then the derivative of x squared over sine x with respect to y, that part's going to zero out, right? And then the other part's going to be 1 over sine x times the partial with respect to y of y squared. So what am I going to get?
2y sine x, or 2y over sine x.
Good. I'm going to get 2y over sine x. Cool. Where is that continuous?
Same places.
Yeah, the same places. And remember too, right? Up here when I was solving sine x equals 0, that was the spots where this wasn't continuous, right? You guys with me on that? So same thing here. So this thing's going to be discontinuous when sine of x is 0. That's going to be the same set of x's. And so the answer to B is going to be the same as it was to part A. You guys see that? Which means that everywhere the solution exists, it's going to be unique. You guys kind of on board with that?
Yep.
Okay, cool. Did that answer your question, Jordan?
Yeah, thoroughly.
Okay, cool. Thoroughly. He says when he's bored listening to the response.
I had a really hard time with this section too, but mainly because I forgot the Newtonian notation for partial derivatives. So when I saw the f sub y, I was like, what the hell does that mean?
When
Oh,
did we learn that?
Yeah. Yeah.
yeah, I suppose I should maybe be completely fair because I think I probably have a couple people in this class every semester that haven't had multivariable calculus. So what we're doing here is we're differentiating this as a function of two variables with respect to y, which means that we're treating all of the x's as constant and just differentiating with respect to y. And then this thing is sometimes denoted as fy or as the partial with respect to y of f, or as the partial of f with respect to y, depending on kind of where you're at. Yeah, that's Bridget, it's been a while for you. Was that notation okay for you?
Yeah, I'm good on partials, but it's been like a decade. So a little fuzzy.
Yeah, no worries. All right.
Can you explain your notation for when it's discontinuous? You have for n within ZXC.
Oh yeah, that's a capital Z. So that's
Okay.
that is this symbol, which is a big ass Z with a double bar and a little thingamahoo.
Okay.
And this traditionally means the set of numbers. So kind of the counting numbers, the negative counting numbers. Oops. Probably want to include 2 in that set, Joe. So counting numbers, negative counting numbers, and 0.
Okay.
And this thing is kind of called blackboard bold.
What?
So if you look in the textbook, it'll just be a big capital Z. It probably won't have this kind of funny hieroglyphic thing going on.
Cool. Thank you.
Depends on which book you're reading. Some people actually like that blackboard bold so much that they'll render it.
Like I think LaTeX and Unicode both have like a double Z character that you can use.
Yeah, in LaTeX, there's actually a font package called Blackboard Bold that you can use to render all the letters that way.